Welcome back, everyone. In this video, we will prove that there are infinitely many prime numbers, and it will be the first video in a series on number theory. So let's begin. We'll begin by supposing that there are finitely many primes, and we'll call them P1, P2 through Pn. What we're going to do is we're going to take these primes, consider their product, right? We're going to multiply all these primes together and we're going to add 1 to it, and that'll be a new number. So we'll say construct the number P, here I'll write on the next line, P equals P1 times P2 times ... times Pn. Awesome. So we've constructed this number and we're going to take it and we're going to add 1 to it. Okay. Note one thing about this number, and that's that it's not prime, right? All of our primes are right here, P1, P2 through Pn. That's all of our primes. So P, note, P cannot be prime. So I'll just say P is not prime. Okay, so P is not prime. That means that it's composite. So since P is composite, P must be divisible by at least one of our finite list of primes. So let's call one of these primes that divides P sub m. So P sub m divides P. Now if you think about it, you can kind of see why we have a contradiction now. So we have that P must be divisible by at least one of our primes P sub m. Remember, P sub m lives somewhere up here. We don't know which index we're talking about, but P sub m is one of these primes, right? And we're saying because this is the list of all the primes, P must be divisible by at least one of our primes. P must be divisible by at least one of our primes. Because there are finitely many primes, therefore this number P is not prime, and therefore P must be divisible by at least one of our primes, and we're going to call it P sub m. But again, this is a contradiction. P is divisible by P sub m, but also when we take P sub m and we divide it into P in this expression, we get a remainder of 1. So note, we're saying here that it must be divisible, which means a remainder of 0, but then looking up here, we see that we have a remainder of 1. So therefore, we have a contradiction. So usually people note that with these arrows pointing at each other like this. That means that we have a contradiction. And because we assume there were finitely many primes and we arrived at this contradiction, it must be the case that there are, in fact, infinitely many prime numbers. So that is the end of the proof.